Hello everyone, this video is about Chapter 2, Methods for Describing Set of Data, Part 2, Methods for Describing the Quantitative Data. To describe the quantitative data by graph, we also have three methods: dot plots, stem and leaf discipline, and histogram plot. Here is an example of a set of data of EPA mileage ratings on 100 cars. A dot plot for the 100 EPA mileage ratings is shown in this figure. The horizontal axis of the figure is a scale for the quantitative variables. The numerical value of each observation is located on the horizontal scale by a dot. When data value repeat, the dots are placed above one another vertically. Another graphical representation of the data is stem and leaf discipline. In this discipline, the left side is the stem and the right side is the leaf. Step 1. Rank all the data from smallest to largest. Step 2. Select a reasonable stem. For the unit of the stems, usually in ones, tens, 100s. You should define the unit of the stem. For example, if you define the stem unit as ones, then 30 here will be 30. If you define the stem unit as tens, then 30 here will be 300. Step 3. Enter every value as a leaf. Remember, only one number in the leaf side, so numbers may be truncate or rounded. Note that please leave empty stems empty if there is no number here. Do not write as 0. If you write as 0, it means that there exists a number 43.0. Here are two examples of the methods of truncate or rounded. For number 24.7894, it can be truncate as 24.7 or rounded as 24.8. For number 52.2367, it can be truncate as 52.2 or rounded as 52.2. Now I'll introduce another graphical method, histograms. Let's see the steps for this. Firstly, find out the maximum and minimum numbers. Then the rank of the x-axis will be maximum minus minimum. After that, create reasonable class intervals, usually in ones, fives, tenths, or 100s. Note that all the class intervals should be the same width. Lastly, count the frequency, how many, for each class interval on the y-axis. Now, we've examined some graphical techniques for summarizing and describing quantitative data set. We turn to numerical methods. Mean, median, mode are three numerical measures of central tendency. Here is the definition of mean. We have population mean and sample mean as follows. Mu is the population mean, where sigma is the summation of all x value and n is the number in the population. Sample mean is denoted as x bar and n is the number in the sample. The median is defined as the middle number when the measurements are arranged in order. So firstly, order the values from the lowest to highest. If n is odd, find out the middle number. If n is even, find out the middle two numbers, and then take the average of the two numbers. Sometimes the dataset will be skewed if one tail of the distribution has more extreme observations than the other tail. If the mean is on the right side of the median, we say that it is right skewed. That is, mean is larger than the median. If mean equals to median, the dataset is symmetric. If the mean is on the left side of the median, we say that it is left skewed. That is, mean is smaller than median. A third measure of central tendency is the mode of a set of data. The mode is the measurement that occurs most frequently in the dataset. Here are three examples. In the first dataset, 5 occurs most frequently, so the mode is 5. In the second dataset, both 4 and 5 occur most frequently, 3 times, so the mode is 4 and 5. In the third dataset, all the values occur the same time. Then we say no mode. So mode can be more than one number or no mode. Measure of central tendency provide only a partial description of a quantitative dataset. We need a measure of variability as well as a measure of central tendency to describe a dataset. There are three numerical measures of variability: range, variance, and standard deviation. Perhaps the simplest measure of the variability is its range, which is equal to the largest measurement minus the smallest measurement. The range is easy to compute and easy to understand. Now, let's see a measure which is more sensitive than the range: variance. We will have population variance and sample variance as follows. Sigma squared denotes the population variance, where sigma here is the summation of all x values. And then divide by n the number in the population. The sample variance is a bit different, divided by n minus 1. Here is another method to calculate variance, which we call a shortcut formula. The same here. For population variance divided by n, and for sample variance divided by m-1. The standard deviation is just the square root of variance. Sigma denotes the population standard deviation, and S denotes the sample standard deviation. Actually, from the notation, you can tell the relationship of variance and standard deviation. The variance equals to the standard deviation squared. Oppositely, the standard deviation equals to the square root of variance. Now, you can practice using the calculator. If you are using TI-83 or TI-84 plus calculator, you can follow the instructions step by step. We will use the STAT button. Note that if you are using the STAT button the first time, the L1 is empty and you do not need to clear. If you use the second time, the calculator will keep the previous data and you need to clear first. Please follow the instruction and try to enter in the same dataset as the instruction and see whether you can have the same result in your own calculator. Remember, the population and sample standard deviation are different. Your calculator does not know that your data are from a population or a sample, so the calculator gives you the both result. You need to choose yourself. For sample data, you need to choose SX as the standard deviation. For population data, you need to choose sigma x as the standard deviation. Most of the time, we will deal with sample data while you choose SX mostly. The calculator does not give you the variance. You need to calculate the standard deviation squared. In the output result, x bar is the mean. Sigma x is the summation of all the x. Sigma x squared is the summation of all the x squared. Sx is the sample standard deviation. Sigma x is the population standard deviation. N is the number of data. Minx is the minimum. Q1 is the first quantile, which I will introduce later. Med is median. Q3 is the third quantile, while I will also introduce later. Maxx is the maximum. Now, I'll give you the simple summary. Mu is the population mean. X bar is the sample mean. S squared denotes the sample variance, and S denotes the sample standard deviation. Sigma squared denotes the population variance, and sigma denotes the population standard deviation. Here is a way to interpret the standard deviation. Empirical rule. In the empirical rule, the distribution is a bell-shaped distribution where the middle is the mean. It says that 68% of the data fall within one standard deviation. 95% of the data fall within two standard deviation, and 99.7% of the data fall within 3 standard deviations. It's always called 3 sigma rule. However, your real data do not always satisfy the empirical rule. You need to check whether your data satisfy the empirical rule separately. For within 1 standard deviation, calculate the data percentage. That is, use the mean minus and plus 1 times the standard deviation, and you will have a range. Then count how many data fall within this range and divide it by the total number. If the data percentage is bigger or equal to 68%, it satisfies the empirical rule. Otherwise, it doesn't satisfy. For within 2 standard deviations, calculate the data percentage. That is, use the mean minus and plus 2 times the standard deviation, and you will have a range. Then count how many data fall within this range and divide it by the total number. If the data percentage is bigger or equal to 95%, it satisfies the empirical rule. Otherwise, it does not satisfy. For within 3 standard deviations, calculate the data percentage. That is, use the mean minus and plus 3 times the standard deviation, and you will have a range. Then count how many data fall within this range and divide it by the total number. If the data percentage is bigger than or equal to 99.7%, it satisfies the empirical rule. Otherwise, it does not satisfy. Now, I'll use the sample data as an example. From the calculator output result, mean is 68.579 and standard deviation is 17.541. First, within 1 standard deviation, mean minus and plus 1 times the standard deviation is 51.038 and 86.12. Let's count. There are 14 out of 19 data fall within this range. So the data percentage is 14 divided 19 equals to 73.7%, bigger than 68%. It satisfies the empirical rule. Second, within 2 standard deviations, mean minus and plus 2 times the standard deviation is 33.497 and 103.661. There are 19 out of 19 data falling within this range, so the data percentage is 100%, bigger than 95%. It satisfies the empirical rule. 3. Within 3 standard deviations, mean minus and plus 3 times the standard deviation is 15.956 and 121.202. There are 19 out of 19 data falling within this range, so the data percentage is 100%, bigger than 99.7%. It satisfies the empirical rule. Another new definition is percentile. That is, for any set of n numbers, the p's percentile is a number such that p% of the measurement fall below that number, and 100 minus p percentile fall above it. Therefore, it is about the position. You can find out this position by this formula. The 25th percentile we call the first quantile, Q1. The 50th percentile is the median. The 75th percentile we call the third quantile, Q3. And interquantile range, IQR, is Q3 minus Q1. How to detect outliers? You can detect them by graph or by z-scores. We can use box plots as shown. Here is Q1, median, and Q3. Lower inner fence equals Q1 minus 1.5 times IQR, and upper inner fence equals Q3 plus 1.5 times IQR. Outside the inner fence are the outliers. Or we can use z-score to find out the outliers. You can calculate the z-score by these two formulas, depending on the data from a population or sample. That is, x, the number, minus mean, and divided by standard deviation. After you obtain the z-score, if the absolute value of z-score is between 2 and 3, we say it is a normal outlier. If the absolute value is bigger than 3, we say that it is an extreme outlier. Here is a summary of Chapter 2. In Chapter 2, we have learned how to use table or graphs to describe the qualitative data. Also, we can describe the quantitative data by graphs or numerical measures. We have learned 4 graphs: dot plot, stem and leaf discipline, and also histogram and box plot. For central tendency, we have learned mean, median, and mode. For variability, we have learned range, variance, and standard deviation. At the end, we learned percentile and how to detect the outlier using z-score. That's all for Chapter 2.